here. So I want to tell you something I'm working on. So this is actually started like 10 years ago. This is a joint work with quantum field theorists and computer scientists. These people are computer scientists. And he's the person. And so there we actually classify what's called the holographic entanglement entropy inequalities, which I will talk about. And since then, so in this paper in particular, we prove that for each even number of parties, the number of inequalities are finite. And so I've been trying to sort of classify them. And then, but we ran out of idea in human brain. So now I'm working with my students to try to use reinforcement learning to classify entanglement entropy. So let me introduce notation. So when I write A, B, C's, these are parties in the sense of entropy. So these are subsystems that you're considering. And so when you have a combination of two parties, I often write it as A times B just to save notations. And then SA is an entanglement entropy. Entanglement entropy between A and its conflict. Okay, so that's the notation. Okay, so those quantities, the entanglement entropy satisfies lots of interesting inequalities, and that plays a very important part in understanding information theory and its applications. So classically, there is Shannon entropy. And this is a very important point. Of course, Shannon introduced the idea of entropy. He didn't know this was entropy. I think von Neumann told him that it's actually the same as entropy. That he tried to explain how, kind of quantify how much information can transmit it in the information processing. And so this quantifies the performance for information processing tasks. And but it was shown around 2007 that the number of inequalities is infinite for the party greater than 3. Okay, so the Shannon entropy have infinitely many inequalities. Okay, so quantumly, so this is a von Neumann entropy. So actually, in this case, totality of independent entanglement entropy inequalities is not known. But no one played a very important role. So for example, there is a strong subadditivity, which hold this one. And this was a very important discovery by Leibs, Elliott Leibs, and Ruskay. So this is around 1973. So this is called strong subadditivity, often shortened as SSA. And but in general, actually it is expected. So there are some. So here it has been proven that there are infinitely many inequalities. Quantumly, it's not known, but numerical evidence suggests that there are infinitely many of them. So it's very interesting that in my work 10 years ago, we found that in the case of holographic system where ATS CFT works, and you can calculate entanglement entropy in conformal theory using weakly coupled gravity theory. So for this particular types of quantum system, we have proven that actually number of inequalities is actually finite for each number of parties. So I will explain you how we proved it, give you an idea. And moreover, in this paper, actually, we have been able to classify all of them up to 4 parties. And for the last 10 years, several other people try to actually classify these inequality for. By now, actually, we know all the inequality up to 5 parties. But classifying entropy inequality for 6 parties turned out to be very difficult. And so we are going to use machine learning to classify. So that's the idea. Okay. And if you use holography, then actually entropy inequality has a nice geometrical interpretation, such as in terms of triangle inequality. So I would like to explain that. So, so the idea is to use the Ryu-Takayanagi formula. So you might have heard. So I don't have time in 15 minutes to explain what LBH-GFT correspondence, but I hope some of you have heard about it. So you have, when you have a conformal field theory on sphere, then LBH-GFT correspondence says that for some class of CFT, there is a gravitational dual that you can use Einstein gravity to describe the same thing. So if you have a region, sub-region in conformal field theory, what Ryu and Takayanagi showed was that you can actually consider a minimum surface subtending on the boundary of this region, A. And then you can calculate the area of this region, and so that gives you entanglement entropy for SA. So basically, SA is 4 times G Newton dividing the area of this region. Okay. So this is the Ryu-Takayanagi formula. So so what you do is that suppose you have n parties, then you can consider 2 to the n minus 1 different entanglement entropy. Because when you calculate entanglement entropy, you consider a combination of these subregions, and then you can ask whether a particular region is in or out. So you have 2 to the n. So you have 2 to the n dimensional space. And then entropy inequality is a question of which subspace which is realized in terms of the entanglement entropy. So you consider the 2 to the n minus 1 dimensional Euclidean space, and you try to specify subspace in which these are realized as entanglement. Okay, so first thing we showed in my paper with 15 years ago is actually that this space of entropy, is realized in this way is actually a cone in a 2 to the n minus 1 dimensional space. The cone. So namely that, so suppose you have some Euclidean space, in this direction you have SA, and in this direction you have SA, B, etc. And in general you have 2 to the n minus 1 dimensional subspace, and it's actually a cone. And then all possible entropies are realized in the inside of the cone. Okay, so it's easy to argue why this is. So first of all, suppose you have a point in this space which can be realized in an entanglement. Then, for example, you can rescale the metric over here. So then, because it's an area, so the entropy would be rescaled. So that means that from that you can clearly see that it is a linear space. And you can also add, so namely that suppose you have one system which realizes particular conformal field theory, which realizes particular point in this cone. Then you can also have another system which realizes another point on this cone. Then you can actually consider just tensor products of these two conformal field theory. And then the entropy would add up. So that means that the space of all possible entropy realized in this way should be actually a linear space. And so therefore it's a cone. And in fact, it's a convex cone. So I should have written convex cone. Because you can add them. Okay, so this is interesting because then the finding the task of inequality is the same as finding all the facets of this entropy cone. Okay, so that's the first step. And the next thing we did in this paper is that we proved that actually this entropy cone, holographic entropy cone, excuse me, entropy cone is rational polyhedral. Okay, so it actually not only the cone, but it's a rational polyhedron. So namely that there are only finite number of independent entropy inequalities, which is in contrast to this general quantum case. Okay, so how do we prove this? Well, so you have this subregion, so you can have A, and you can have B, and you can have, say, C, and then there are some complement regions. And then according to Ryu-Takayanagi formula, you consider these subspaces like this. And then, so for example, if you have, you can consider various inclusion and exclusion. So for example, if you want to calculate entanglement entropy for A, you consider this minimum surface. If you want to calculate entanglement entropy for B, you consider minimum surface. If you consider entanglement entropy for A union B, you consider this region, etc. So then what you can do is you consider dual of this configuration. Namely, that can you see blue? So you consider each of these regions by taking the dual of this in terms of vertex, like that, and then you connect them like this. For each minimum surface, you connect them. Okay, so then what you can easily see that for each edge, you can assign the area of the corresponding regions. Okay? So therefore, in this way, you can have a graph model. You can have this kind of discrete geometry. You have a graph model. To calculate entanglement entropy. Okay? And so rather than calculating concerning complicated bulk geometry, we can consider this kind of graph model. And so each of these blue lines correspond to a segment of Ryu-Takayanagi surface separating these regions. So then what we're going to do is to consider what we call the minimum cut. So namely that, so if you are, for example, interested in some boundary region, which can have A1, AI1, A1, I2, etc. So suppose you have some kind of region, then what you're going to do is to consider a minimum cut. Separating A and A bar by considering combination of these vertices. And so then discrete entropy is given by minimizing all these possibilities. Okay? So conversely, you can also show that you can actually prove, so this requires some proof, that so I have shown you that for each configuration, for each geometry in the bulk, you can construct a graph. But you can also prove, and this requires some knowledge of hyperbolic geometry, that for each graph, you can actually reconstruct the hyperbolic geometry in the bulk. And then for each given time, so then it becomes a finite problem. Because for each number of parties, you have a graph of finite number of vertices, and then it's just a minimization program. So then it's clear that the corresponding constraint should be finite. So that from this, you can actually prove that the holographic entropy cone is rational polyhedron. Okay, so that's the idea. So in practice, then what we're going to do is, in practice, what we're going to do is the following. So we try to find, this is a finite dimensional, so we try to find inequality in a finite process. And so even though, however, the number of independent inequalities is finite, it may be computationally heavy to perform them, to search for them in brute force. So what we're going to do is that in practice, we guess inequalities and check whether they are true inequality or not by constructing the corresponding geometry. And but then, since we are guessing the inequality, you can ask, well, how do we know that we have found all the inequality? How do we know we have found all the inequality? So have we found everything? So we have an answer to that, which is that we can actually, if we can construct extremal rays, if you can construct extremal rays, then we have done the task. So namely that the following we have the so since we are considering this discrete geometry, we have the following cone. So delta T equals the extremal ray. These are the rays in this convex cone that cannot be written as a proper convex combination of other elements in this cone. So what in practice we're gonna do is that suppose we have a candidate for the holographic entropy cone. Then what we're gonna do is that we can calculate all the extremal rays defined in this way. And for each ray, we try to find the bulk geometry. Namely, in practice, what we're gonna do is to try to construct this kind of graph. And then if we can construct the graph which realizes the extremal rays, and we can do that for each extremal ray, then we are done. Okay, so that's, and then we have classified all the entropy inequality. So that's one thing. Another thing we need to double check on that is to see whether given entropies, inequalities hold for all the physical systems satisfying the physical holographic construction. So namely that how do we prove that it holds for all holographic states? So let's see, how am I doing time? Do I have like 5 more minutes or so?
Yes.
Okay, good. So there is actually, so this was the most difficult question we faced. And then we actually came up with a very efficient method called proof by contraction. So let me see if I can explain this. So suppose let's say the strong subadditivity. So strong subadditivity inequality is like this: SAB plus SBC is greater than or equal to SB plus the SABC. So this actually not only for holographic system, but for any quantum polynomial entropy. This was proven by Lee and Sky. And so for this, I introduced the following notation. So you have X and Y. So you have the following things, and I define SA, XA to be a two-dimensional vector 0, 1, and YA is equal to 0, 1. Okay, what I mean by it is that here A is included in the first entry and not included in the second entry. Right? And here A is not included in the first entry and A is included in the second entry. So I define a two-dimensional vector in this way. YB is equal to 1, 1, etc. So I define this vector. And then what we see is that with this notation, this can be written as SAI alpha I is equal to or greater than R of SAR beta R. And so what we have, so the proof by contraction is the following things, that the inequality of this type is a valid holographic entropy. So this is a valid one. If and only if, so you can actually prove this by repeatedly doing triangle inequalities. But you can prove this provided that if there is such a map F, which maps 0, 1 to L to 0, 1 to R, such that X minus X prime measured in the metric on the left-hand side is greater than the image. Okay, the detail is a little bit complicated, but we can actually prove that once you find an inequality, we can check whether all the inequalities are satisfied, and all the holographic states satisfy this. So this sort of completes the task, and so in principle, this is a finite task. Okay, so we actually carried out this task for 3 parties, 4 parties, and then the subsequent paper actually classified for all the entropy inequality for 5 parties. So in this way, this framework successfully classified holographic entropy inequalities for up to 5 parties. But however, it faced fundamental challenges in going to higher number of parties. For example, if you want to do it for 6 parties, we have to actually do this for 63-dimensional space. And the contraction method can easily prove the validity of individual inequalities, but confirming that search is exhaustive and complete in such a high dimensional space is challenging. So what I did was first send one of my graduate students for an AI company in San Francisco and have him trained for a quarter and brought him back, and then we started working on it. And to overcome this challenge of completeness verification, what we did was that we developed a reinforcement learning approach. So our reinforcement learning agents are trained to determine if target entropy satisfies the holographic constraint by learning to construct the corresponding quantum gravity computation. Namely, what we trained the AI so that for given entropy vector, so for any entropy vector, the machine tries to reconstruct the quantum gravity geometry in terms of graph mode. Okay, so that's actually we can easily train machine to do that. And of course, it's not, machine cannot always construct it, because the thing is that if the target entropy is inside of the correct entropy cone, then you can actually construct the correct geometry precisely. So this is how machine learns it. But if the target entropy is outside of the cone, by definition, there is no geometry. There is no graph model. So machine should not be able to construct it, but machine learns how to do it. So try to do as best as you can. So then there is an error. So basically what we did is to use that error as a reward function and try to actually minimize that function. Okay? So basically if the configuration is found, it means the target entropy satisfies the constraint, and so that the reward function is maximum. And but if no valid configuration exists, because target entropy lies outside of the constraint, our optimized reward function provides a continuous landscape that measures the proximity to the boundary to saturate entropy inequality. So basically, since we have the reward function, once you are outside, the machine can see how you can go inside of the cone. So this allows us to compute a local gradient that guides the machine to go toward the genuine boundaries. And so this approach offers this systematic method to complete verification of entropy inequalities for large number of parties. So as a proof of principle, actually we have successfully demonstrated that this framework is able to identify all the holographic entropy inequality up to 3 parties, and then we went out to apply that for 6 parties, and that's what we are working on. And we have already found the new inequalities. There are, for 6 parties, there are many unknown inequalities. And in fact, machines have been able to actually identify the true inequalities that were not known. And so I think this demonstrates that the feasibility and usefulness of our reinforced learning framework in high-dimensional entropy space. So our immediate goal is to classify all the holographic entropy inequality for 6 parties by doing this in terms of machine learning. And I hope, so actually, the entropy inequality that are satisfied only on the holographic system actually gave very important insight into quantum gravity. For example, for 3 parties, there is a thing called the monogamy of mutual information. That was actually very important in identifying the firewall paradox in black hole. But ultimately, we aim to achieve complete classification of all number of parties using this method. Okay, so thank you. That's all I want to say.